Hello everybody. So in this module we will focus on explicit design methods. What we saw previously was several controller components, like there was a proportional controller, there was a derivative controller, there was an integral action, and we had analyzed when, under what situations do we need a derivative component, under what situations do we need to add an integral component, what are the effects of adding zeros to the system, what are the effects of adding extra poles to the system. Like for example, in terms of the root locus, what we had seen was adding a 0 has the effect of pulling the root locus further to the left, and the more the root locus is further from the imaginary axis, the better the transient response, right, so to speak. And there are also methods where if I add an integrator or a pole at the origin, I could derive that the steady state errors go to 0. But we need to be careful, because what we saw with the help of few examples is that just blindly adding integrators might even lead the closed loop system to be unstable. So we'll formalize those things a little more. So what we studied earlier was the entire analysis based on dominant closed loop poles. Say for example, if I have 10 poles in my system, all the analysis could be based on the poles closest to the origin, because that is what really decides the behavior of the system in the long term, because the other poles which are to the left, their response actually dies down pretty fast. So for example, if I just take a system which has 2 poles here, some guy sitting here, 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 and so on. So the pair of poles which decide how my system behaves more or less can be approximated by just looking at these 2 poles, because these transients die out pretty quickly, because we are looking at something like exponential of some number k times t. Bigger the k, faster they decay. Smaller the k, the slower they decay. So this actually corresponds to smaller k. And if you see that if they are on the imaginary axis, then these guys never decay. It's a constant oscillation process. Okay, so we also looked at issues in implementation of the nominal derivative or PID controllers, right? So in a way that if I just take a P and D controller, we saw that it cannot be realized physically, as it is a non-causal systems. So this will lead us to have slight modification of these components in terms of physical realizability. Like for example, I can never have a perfect integrator, right? So this kind of systems are very difficult to realize in real world. So an approximation could be to classify PD controllers as lead compensators and PI as lag compensators. Compensators also means controller. So whenever I say compensator, it also means controller and vice versa, right? And okay, so given a system, how are the performance criterion specified? How is the performance criterion specified? It's usually specified in terms of some kind of peak overshoot, some kind of settling time, and so on. And these loosely translate with some, we know the formulas, that these are specifications of zeta and omega n, and I can construct the dominant poles based on this, right? And we see that these are how these are related both in the time domain and the frequency domain. Like there is a direct one-to-one relationship between the phase margin and the damping coefficient. So here we will see explicitly how we construct these lead and lag compensators, and the tool we will use for our analysis is the root locus technique. So we will make use of the root locus plots which we learned to design lead and lag compensators to meet a certain performance specification. Okay, so in a typical closed loop system looks like this. So I am given a plant g of s, and suppose g of s does not behave the way I want. Well, the constraint is that I may not be able to alter the plant, or it might just be expensive. In some cases, it may also happen that a proportional controller may not achieve specifications. In that case, we need to add, so these are like static controllers, right? I'm just increasing the gain. If increasing a gain does not help me, I need to add a dynamic compensator, right, which has some poles and zeros, right, to overcome the shortcomings of the plant in meeting the desired specifications, as simple as tracking a reference signal. Okay, so when I say I am adding a compensator, it essentially means that I will have a system with possibly some gain, some zeros, so on, and some poles, and so on. Again, I will make sure that the number of poles is greater than or equal to the number of zeros to maintain the causality condition. Okay, so we had earlier discussed the effects of adding poles and zeros to the open loop transfer function, right? So now how do I make use of the root locus to achieve this desired performance specification? That's what we will analyze, and all this analysis will be in terms of the dominant pole pair. Okay, so and when I talk of dominant pole pair, it is easy to specify these transient performances through a standard second order system, right? Okay, so how does the second order system look like? I have the transfer function as omega n square, s square plus 2 zeta omega n s plus omega n square, and we know what zeta means. Zeta is a damping coefficient which decides the system is underdamped, overdamped, critically damped, and so on. Omega n is the natural frequency of the system. So a certain step response to the system leads us to these expressions that the peak overshoot is directly related to a zeta, and the settling time depends on zeta and omega n. Similarly, there are formulas for the rise time, the peak time, and so on. Okay, so now given MP, given Ts, these guys would result in a certain zeta, a certain omega n through these formulas. And how would they be related to the dominant poles? So given zeta and omega n, can I actually construct dominant poles? Well, it's just by this formula, right? So how just the poles or the solutions of this system, right? For typically for an underdamped case. Okay, so when I do all this design procedure, and if I just design my system based on these numbers here, I must ensure that this design procedure which I follow in terms of the second order system, these are actually the dominant poles, that these are the poles which are closest to the j omega axis. Okay, so first question is, where are the dominant poles? If I look at it graphically, so given a zeta and given a omega n, I can look at this thing, right? So these are lines which are constant zeta lines, right? And how is this angle theta determined? Theta is cos inverse zeta, and these are lines which have constant frequency. If for different frequencies, I have semicircles here or here and so on, and we had seen this in one of our earlier lectures. So if I am given a certain range of zeta and omega n, say my performance specifications, if they are, say, let the peak overshoot be less than 0.1 or 10%, that will give me a little range of values, right? It's not strictly that it should be 0.1. Similarly for omega n in terms of the settling time. So if I have give some ranges that the zeta should be between this number and this number, or the omega n should be between this number, I will have a range here, right? I can choose any pole within this blue region, right? So if I look at specifications in terms of MP and TS, this translate to zeta being within a certain bound, right? So these are like the zeta lines. So any zeta within this will give me MP less than C1, right? And this you can go anywhere all the way till infinity on the left hand side. Similarly, if I look at the settling time, which is again depending on zeta and omega n, these are the lines, right? This is zeta omega n, and then anything here would meet this specification. How both of these are met is through the area here. Say choose a pole anywhere here, right? Say somewhere here or here, it would meet these specifications. Okay, so the transient performance specifications are usually in terms of zeta and omega n, and the steady state performance specifications are usually in terms of the steady state error. depending on if I am tracking a step or I am tracking a ramp or a parabolic input. And based on these specifications and or these definitions and the type of the system, we had characterized several error constants. So, what we concluded from that analysis is that if it is a type 0 system, which means G will not, or G times GC will not have a pole at the origin, then it will be able to track a step input, but with some error. And we know how to compute this Kp, right, with this simple formula. Similarly, a type 0 system will never be able to track a ramp signal and parabolic signal and other higher order signals. The system is of type 1, which means G times GC has a pole at the origin, then it can track a step input with 0 steady state error. It is able to track a ramp with some steady state error, and it will never be able to track a parabolic signal. And similarly for type 2 systems, it is the steady state error for a step in step reference is 0, steady state error for a ramp input is 0, but for a parabolic input it is some finite number, right. So, this analysis is what we did much earlier in the course. Okay, so let us start with an example to motivate how we will build our case to design a controller. So, let us start with a simple plant 1 over s plus 1, and I interconnect it to a controller in the standard feedback setting, and the transient specifications are that the peak overshoot should be at best 10% or at most 10%, and the settling time should be less than 5 seconds, right. And the steady state specification is in terms of the velocity error constant, that it should be less than 10. Okay, so let's first translate this into the locations of closed loop poles in terms of the dominant poles. Okay, so MP of 10%, I put it into the formula, TS of 5 seconds, I put it into the formula, and I get these numbers. Theta is 0.59 and omega is 1.35. With these two numbers, I get the location of the dominant closed loop poles at minus 0.8 plus minus j 1.0914. Okay, so the first thing to do here would be to see, look at this in terms of the closed loop specifications in terms of the dominant poles. So, first what I would do is see what is the root locus of the system, right. So, it's kind of very straightforward to plot. We have done much more complicated plots than this. This is the point 1 over 2, this is my pole, this is my pole. So, this guy goes here, this guy goes here, and then they will split this way. Okay. Now, I want my compensator to be such that the closed loop poles or the dominant poles should lie on the root locus. This is what the system is. So, if I just look at, well, now, so this is the root locus of G times S, I can just say, well, can I just add a controller K, proportional controller, and check if my requirements are met. How do I do this? I just move along the root locus and see if for any value of K, am I reaching this point, or are these points on the root locus for some value of K. Okay. Now, does there exist a K? Right. So, if there exists a K, then my GC would just be that K, right, just a proportional controller would satisfy that. So, here I can easily see, right. So, this line is minus 0.59, this is minus 1, this is minus 0.5, and my dominant poles are somewhere here. So, what I see here is no matter how much I increase or decrease the gain, I will never be able to reach these points. Okay. So, the thing is that, or the concept here is that this point or these dominant poles should lie on the root locus of the closed loop system. That is how we will make use of the root locus plot to design controllers. Okay. So, more on this will come shortly. So, what we should check is that does the root locus of the system pass through the desired pole locations? The answer is no. Another way to check is also the angle criterion, right? If I just do not know how to plot, I do not have MATLAB with me, I will just check what is the angle, right? So I am looking at the given dominant pole, and I will always denote this as SD. Okay, now does this lie on the root locus of the closed loop system? And I know that a good way to check this is that the angle of the compensator or the controller plus the plant should satisfy this condition, plus minus 180 blah blah blah. Okay, so if my controller is just a K, right, and then G, I know what is at which point I am checking the angle is at this guy, G times SD. Now this turns out to be minus 205.85, which is not 180. Therefore, there will never exist a gain K such that K times G at SD is 180 degrees. Okay, so just by adjusting the gain, we are not able to meet the desired specifications, right? Okay, another way to find out is just look at the intersection of the constant zeta and the constant omega n line, and that intersection turns out to be this one, right? Just to find graphically the dominant or the desired closed loop dominant pole pair, and it is easy to check that these are not on the root locus, right? But what we would need is these points, the one in the reds here, to pass through the root locus of the closed loop system, which is GC times G of S. Okay, so which essentially means I want to pull the root locus to the left. And if I remember what I had learnt in module 7 is add a 0. Add a 0 so that it will be to the left. Now how much, where to place the 0 is first question. I say okay, add a 0, do I really add this blindly anywhere? So this is the question which we will try to answer. Okay, so before I know where the 0 will be placed, I'll just recollect what I observed earlier in terms of the effects of adding a 0 to a system, right? So okay, I just have the standard system. This is my given plant, 1 over s plus 2, s plus 5 has a root locus like this, right? So for certain gains it goes to instability. Okay, let's say I add a 0 at s equal to minus 7 somewhere here. Then I see that the root locus is pulled slightly to the left. That okay, I am actually ensuring stability here for certain values of k, or for certain values greater than this number. My system is becoming unstable. Here my system is stable, right, for all values of gain k, or at worst it is marginally stable. However, this is a system which has a very low relative stability. The slight changes in system parameters can actually push this to the right and lead to the verge of instability. Okay, so I'll add a 0 further to the right, right? So at s equal to minus 3. Now see, okay, some nicer behavior here, right? That this is a system which has a bigger stability margin than this one. And finally, if I add a 0 at s equal to minus 1, you see, well, it has something more, so something much better in terms of the relative stability. Not only that, if I say that the transient response of this system would be much poor compared to this system, right? And this root locus is further to the left of this locus, so this will have a better transient response. Okay, so the effects of adding a 0 is to pull the root locus to the left, here, further to the left. Now, thing is, how much to pull? The how much to pull is answered in a way that you pull it just enough so that this SD, the dominant pole lies on the root locus of G times Gs or Gc times Gs. Okay, so the first thing which we would like to see is how much do I pull? Well, you pull just enough such that it meets the angle criterion. And the angle of my compensator evaluated at SD, angle of my plant evaluated at SD should be minus 180. Okay. Now, what is my plant? My plant has a pole at the origin and a pole at minus 1. Okay. So, now I compute the angle contribution to SD through each of these poles, at pole at 0, pole at minus 1, okay, and I get a certain number. So, the difference, so what should this GC do such that the total is 180, that it should make the required adjustments in the angle of G of SD such that the total is 180, okay. So, let me call this angle as phi, right. So, phi plus angle of GSD should be minus 180. If the angle of GSD by itself is minus 180, I do not need to do anything here. The compensator need not add an extra angle, right. So, in this example, it turns out that the phi should be 25.8 degrees. You can just, these are very simple computations, okay. So, this compensator or controller must contribute an extra angle of this one, and therefore, I call it a lead compensator. It adds an angle to the root locus, okay. Now, let me just assume, without really worrying about if I can realize this compensator or not, let me just do some analysis before I really have a constructive way to determine how the lead compensator looks like. So, let us say my compensator just is a proportional plus derivative controller with the same constant, right. Now, let me assume that I just put my 0 at some arbitrary location ZC, and this is what I have to find out, okay. Now, the total angle of GC plus G should be minus 180. So, I just use this little triangle here, right. So, this phi is given to me, phi is this one, okay. Now, theta is also known to me, which comes from cos inverse theta. I also know what is omega n, okay. Now, I know several things here. I know theta, I know omega n, I know this guy. Now, can I calculate what is my ZC? Well, I just use a very simple trigonometric rule, right. So, sine of the ZC over all these numbers would be omega n over sine phi, and just this computation. So, theta is known to me, phi is known to me, omega n is known, phi is known. I just get that the location of ZC is 3.0518, somewhere here, right. So, choosing a 0 at, now I am not really worried about what is this k, because this k does not really contribute to the angle, right, or it does not contribute at all. So, if I place my ZC at this value, then my contribution of angle GC times G is minus 180 degrees. Okay. So, now, okay, how does GC times G look like? GC times G looks like this: k, the 0 which I added because of the compensator, and the poles of the plant. Okay. Now, what is this k? And I just simply cannot choose any k. This k is then chosen by the magnitude criterion, such that the overall magnitude of k times the 0 and the poles should be 1. Okay, and this k can be computed by again looking at what is the gain contribution at SD. So, all these are evaluated at S equal to SD. This is also evaluated at S equal to SD. Okay. So, again these are just simple computations. Okay, now let us see what is happening with the root locus. Well, the root locus, it has a pole here, a 0 at minus 1, sorry, a pole at 0, a pole at minus 1, and the new 0 here, which is the compensator. This is my controller, and I see that the root locus now, which was earlier, which was something like this, right, it was going up here, going down here, has now been pulled to the left in such a way that the closed loop root locus actually passes through this point. Okay, so how does now the plot look like, or the response look like? Well, this is my compensated system with the closed loop transfer function gc times g 1 over gc plus g. We know how to derive this binomial. And the compensated system has a peak overshoot, if I compute, of 11% and a settling time of 4.08%, which are more or less what we wanted, right? So the system has a 0 here, right, this along with the dominant poles. Okay, now let us see how close are these two plots. First, all my specifications are in terms of dominant second order. This is a little redundant, I am writing second order, but still just for completion, right? Dominant second order poles, right? So what I designed in terms of zeta, omega n and zc and the appropriate k were only was in terms of just taking the response of a standard second order system. Okay. Now in addition, I add the compensator, so I have, in reality this is not true, right? So my dominant pole analysis is based on this kind of transfer function 2 zeta omega n s plus omega n square. Okay. Now in addition, I have a 0 here, right? So I have the plot will be the plot will include the dominant second order poles for sure, plus the effect of 0. Okay. Now, well, what is the effect of 0? Well, there is some not very good thing happening here, right? If I just draw a plot of the dominant second order system, which is without considering the effect of 0. This is how my design goes, right? All my specifications are translated to a second order system. This is how I would want to look like in the black line. Okay. But however, the compensated system has a 0 at this number 3.05 and so on. Okay. So the compensated system now has the response which is like this, right, the blue line, and therefore you see, well, there is slight increase in overshoot than what I actually wanted. So what I designed is for this. We designed for this dominant poles, thinking that the closed loop system would actually have only this kind of dominant poles and the other guys wouldn't matter much. However, the actual response has a 0. So so this is not the completion of the design process, because there is some gap here, right? This does not really ensure complete dominance of the desired pole locations. So we would want to select the 0 such that these two guys come as close as possible, right? And this will be clear in the slide. So this is still not a constructive procedure to design a lead compensator. This is just by following steps of what we had learnt earlier, that if I want my transient performance to improve, I need to pull the root locus to the left. I can pull the root locus to the left by just adding a 0. Where do I add a 0 is given by this angle and the angle criterion and the magnitude criterion. Now once I add a 0, is it really dominant? Well, you see here it's actually close to dominance, but just that, well, there's a little error, right? So the actual system, this has 11%, so this has 10% overshoot, but this guy has 11%. So we'll try to see how we minimize this gap. That also we should be careful of. Okay, so now we will see. So the response so far is, okay, we looked at dominant second order systems, which should say, just as for example, consider a system like this with a 0 somewhere here. Now we will see, so what we wanted this plots in blue and black to be as close as possible. Now are they related in any way to the location of zeros? If they are closer to the origin, is it good for me, or if they are further away from the origin, are they good for me? So this is the kind of response I am looking at. Okay, so let's start with this system and say I am adding a 0 at s equal to minus 0.5. Okay, so this y1 is the step response of this guy, okay, and y2 is just adding a derivative, right, y1 dot, and y is a total response, right, this y is the total response. Now I am adding a 0 at minus 0.5, and okay, so now I add a 0 at s equal to minus 1, and I see that the red and the black lines actually are coming closer to each other, right. So the red is the response of G prime and the black is the response of G, and I want to place the 0 such a way that these two are closer to each other. And if I put it further back at s equal to minus 8, then actually see that, well, they are very close to each other. So depending on the location of the zeros, my red and black curves come closer or go further away. Okay. Now another effect of adding this 0 is that, well, there is no significant change in the settling time. Okay. In addition to say that, well, this actually the response here is faster, right, this is slower to respond. The black line is slower, I pull the root locus to the left and I see faster response, but faster response will also lead to increase in overshoot, right. And in the limiting case, as a goes to infinity, the contribution of the 0 decreases and we get back the original system behavior, but we really do not want a to be so large enough that it does not really matter, right. So we need to come to a nice trade off of what is a good a to select. Okay. So once I know the effect of adding a 0, there is some drawback here, that, okay, can I just go to the market and buy a controller which looks like this? Well, the answer is no. We had seen earlier, because this is a non-causal system, right. Okay. So somebody, I think in the message forum also asked, what is the inverse Laplace transform of S, and well, the answer is that it does not exist. Okay. So therefore, to make it realizable, we add a compensating pole in such a way that the effect of adding this pole is just for construction purposes, just for practical purposes, but this guy should just keep quiet, should not really try to interfere too much in the process. Okay. So now this compensator, so this again, the angle of GC and angle of G should always be 180, all those conditions should be satisfied. Okay. So if I say that, now earlier only the 0 had to contribute certain angle, now I have a 0 and a pole, so these two together should contribute an angle phi, right. So this is my SD, mu1 is the contribution of ZC, mu2 is the contribution of PC. So this GC will now have angle contribution because of the 0 and because of the pole, and the total thing should satisfy this one. Okay. Now this should always contribute a positive angle, right, which means the angle, this guy should always be greater than 0. Okay. So earlier we see that in the example phi was some 28 degrees, this always contributes a positive angle, and for it to contribute the positive angle, the pole should be to the left of 0. Okay. Not that I have a 0 here and I have a pole here, no, this will not work for this reason. Okay. Now this first conclusion here, before we go further, is that I just cannot have only a ZC, I need to place a pole. Where do I need to place the pole? Is to the left of the 0. Why? Because of this condition here, the positive angle condition, right. Now we will slowly see, okay, where should this guy sit and where should this guy sit, right, and that we will do in the next lecture, right. So far what we have learnt is the effect of adding a 0 helps me in transient response or improving the transient response of the system. I cannot realize a 0 by itself, so I add a pole to make it physically realizable. Now we will try to ask a question where to place these poles and zeros given a certain performance metric. So that we'll do in the next lecture. Thank you.